All right, now we need to use that equation to show that P has an inflection point when P is 25. So inflection point is concavity. That means I have to go looking for the second derivative. This equation gives me information about the first derivative. So I'm going to implicitly differentiate to get information about the second derivative. So I'm going to rewrite this equation. dp dt is the same thing as p prime. And then I'm going to write this as 1/10 p times 50 minus p. And then I'm going to differentiate both sides with respect to time. On the left-hand side, this becomes p double prime. And the 1/10 is a constant. I'll bring him out. And I take the derivative of this guy, which is a product of two functions of t. So the derivative of the first with respect to t, that's called p prime, times the second, plus the first function times the derivative of the second. The derivative of 50 is 0. That's negative p prime. That's 1/10. Now, to simplify this, I'm going to replace p prime with what I know it to be. Remember, dp dt is another name for p prime, with this quantity. So I would have p times 50 minus p over 10 times another quantity of 50 minus p. That's going to make that squared. This negative comes out to make it a subtraction. p times 50 minus p over 10. So I'm going to have another factor of p, makes that p squared. I got 50 minus p over 10. Now I factor out what's in common. I've got a denominator of 10 I can factor out. So that's 100. What can I factor out of the numerators? Well, I've got a factor of p in both and a factor of 50 minus p. And let's see what's left over. Well, from here, I'm going to be left with a quantity 50 minus p, and for here I'm going to be left with the quantity p. And so I get p double prime is equal to 1 over 100 times p times 50 minus p times 50 minus 2p. And this is what we're going to use to analyze the concavity and get our inflection point. All right, so we know from our earlier analysis that p is always between 0 and 50. And so as we've argued before, this quantity then is always positive. And so when I divide it by 100, this is also always positive. So the only thing that's going to affect the sign of p double prime is this guy right here. So if I do the usual analysis, p double prime of t equal to 0, the only thing that matters is this quantity, 50 minus 2p equals 0, and that gives me p is 25. All right, now what I would like to do is to check the concavity on either side of p is 25. To show that it's a genuine inflection point. Remember, to be an inflection point, I need to change concavity. Now, normally when you do a sign diagram, you plug in the independent variable t. We're plugging in the dependent variable p of t. Now p, I'm not going to write it down again, but p is a function. It's differentiable as many times as you want anywhere, so there's no domain issues at all with this. The domain that we're on, though t is bigger than or equal to 0, and as we saw, it starts off at p, when t is 0, the p is 10. So I'm going to use 10 as one of my test values. And I know that the limit as t goes off to infinity of p of t is 50. And so I know at some point, because of the intermediate value theorem, I've got to go from 10 to 25 up to things appreciably closer to 50, so I know that I can go ahead and choose, say, p equals 40 as another test value. Now, when I plug those in to p double prime of t, once again, this is always positive. And when I plug 10 into this, I get a positive number, which indicates I'm concave up for those values of p. And when I plug in 40, I get a negative number, which indicates I'm concave down for those values of p. So that proves that I actually do have an inflection point when p is 25. So that'll do it for part E. All right, so last but not least, part F, we're asked to sketch the graph of y equals p of t. So I'm on the yt axis. And let's write out what we know. I know that when t is 0, the population's 10. So 0, 10 is the y-intercept. The domain, once again, t is bigger than or equal to 0. I know that as t goes off to infinity, I know that it approaches 50. I also know that p always lives between 0 and 50, so everything's happening in here. I know that at 25 I have an inflection point. And I know that happens very early on, like at 0.27, so that the scale is going to be exaggerated here. Oops. So the t-scale is going to be skewed. Let's go ahead and mark that. And I know that from 0, I know that it's always increasing. And I know that it's increasing in concave up for the y values 0 to 25. So I know it's got to be doing this. And then once I get to 25, it's still increasing, but now it becomes concave down. And then it approaches. So I'm not drawing this very well. So it's increasing, concave up, and then it changes to increasing, concave down, and it looks something like that. Okay? And that's a standard logistic kind of graph. That'll do it for part F, and that'll do it for quiz 5.